The golden ratio. The ancient Greeks felt that some rectangles were too fat. Wah! It's practically a square. And some were too thin. What could you possibly do with a rectangle like that? But rectangles with a particular ratio between the height and the width, known as the golden ratio, were the most beautiful of all, called golden rectangles. They filled their architecture with this. The side view of a temple was going to be a golden rectangle. The spaces between the pillars were golden rectangles. And in fact, the average everyday piece of paper that we use is remarkably close to a golden rectangle. If you've ever used legal paper, it just seems wrong. It's too long. It's just a very comfortable rectangle. Anyway, the key to the golden rectangle was that adding a square to one side would preserve its beautiful ratio. That is, if, hypothetically, this is a golden rectangle with some width and height, then if you took that rectangle and you added a square at the bottom, this length is x, so if you added an x by x square, that this would be a golden rectangle as well. Now, to properly compare these two, we should rotate it like so, and you'll see that this would be, if I did freehand draw a golden rectangle, and I did this all correctly, then this rectangle is just an enlarged version of that rectangle. But the overall ratios are the same. That is, that the width x is to the height y, as this x plus y is to x. And we will use that equation in the next video to exactly figure out what the golden ratio is. But for the moment, let's talk a little bit about why I'm talking about this in the middle of fractals. You see, if you were to take a golden rectangle, not only does adding a square on continue to make it a golden rectangle, but taking a square away will do the same thing. This is a golden rectangle, so if you chop a square off of it, what remains will be a golden rectangle. So this is just a shrunk version of the overall thing. If I freehand do this correctly. If you chop a square off of that again, you get another golden rectangle. Chop another square off, you go to another golden rectangle. If you kept doing this forever, you would get a fractal, would you not? This little square in here is exactly the same. This square with the golden rectangle on the right is the same as this if you were to subdivide it forever. And you would have to keep going and going and going and going forever. And not only is that, but watch this. There's a really cute thing. If you put a semicircle in the first square and a semicircle in the second square, well, not a semicircle, a quarter of a circle, and a quarter of a circle in the third square, and so on, it continues to be a fractal. It has what is called a logarithmic spiral in it. Logarithmic spiral. Now, I'm supposed to, at this point, tell you that these appear in nature all the time, and the ratio of a person's belly button, the height of a belly button to the overall person is the golden ratio. And I'm supposed to say that nautilus shells are logarithmic spirals, but mathematicians have overreached a little bit on this, and it turns out that the spiral shells of the nautilus aren't actually logarithmic spirals. But this ratio does pop up enough to give the conspiracy theorists quite a bit of fodder that perhaps, in fact, this was so beautiful.